National Electrical Code Section 727 addresses the separation of analog and discrete instrumentation cable runs. This section is essential for ensuring the integrity and reliability of instrumentation systems, especially in industrial and commercial settings. The primary concern behind separation requirements is to minimize the potential for interference between different types of signals carried by these cables. Analog signals are continuous signals that can vary in amplitude or frequency, while discrete signals are digital signals that have distinct on or off states. Mixing these signal types in close proximity can lead to signal degradation, data corruption, and inaccurate readings, which can compromise the performance of control systems and monitoring equipment. The National Electrical Code provides guidelines on how to properly segregate these cable runs to prevent such issues. Firstly, understanding the definitions within Section 727 is crucial. Analog instrumentation cables are typically used to transmit signals from sensors and transmitters that measure physical parameters such as temperature, pressure, flow rate, and level. These signals are often low voltage and sensitive to electromagnetic interference or radio frequency interference. Discrete instrumentation cables, on the other hand, carry digital signals used for control functions such as starting and stopping motors, opening and closing valves, and activating alarms. These signals may also be susceptible to interference, but the nature of the interference and its impact can differ from that of analog signals. Secondly, the code specifies methods for achieving physical separation. This can involve using separate cable trays, conduits, or raceways for analog and discrete cable runs. The distance between cable trays or conduits carrying different signal types is also specified to minimize interference. In some cases, barriers or shielding may be required to provide additional protection against electromagnetic interference. Thirdly, grounding and bonding practices play a critical role in minimizing interference. Proper grounding ensures that all metallic components of the cable management system are at the same electrical potential, which reduces the likelihood of ground loops and circulating currents that can induce noise in signal cables. Bonding involves connecting different metallic components together to create a low impedance path for fault currents, which helps to protect equipment and personnel in the event of a fault. Fourthly, the type of cable used can also affect the level of separation required. Shielded cables provide additional protection against electromagnetic interference and may allow for closer proximity between analog and discrete cable runs. The shielding effectiveness of the cable is an important factor to consider when determining the appropriate level of separation. Fifthly, the National Electrical Code addresses the use of cable trays for instrumentation cables. Cable trays provide a convenient and organized way to support and route cables, but they can also create a pathway for electromagnetic interference if not properly designed and installed. The code specifies requirements for cable tray fill, spacing, and grounding to minimize interference. Sixthly, conduit systems offer another option for routing instrumentation cables. Conduit provides a physical barrier that can protect cables from damage and reduce the potential for electromagnetic interference. The code specifies requirements for conduit size, material, and installation to ensure that the system is effective in minimizing interference. Seventhly, raceways, including surface raceways and underfloor raceways, are also commonly used for instrumentation cables. These systems provide a flexible and accessible way to route cables, but they may not offer the same level of protection against electromagnetic interference as conduit systems. The code specifies requirements for raceway construction, installation, and grounding to minimize interference. Eighthly, when running instrumentation cables in close proximity to power cables, additional separation may be required. Power cables can generate significant electromagnetic fields that can induce noise in signal cables. The code specifies minimum separation distances between power cables and instrumentation cables to minimize interference. Ninthly, the use of filters and surge protection devices can also help to mitigate interference. Filters can be used to block unwanted frequencies from entering signal cables, while surge protection devices can protect equipment from voltage spikes and transients. Tenthly, it's important to consider the specific requirements of the equipment being connected when determining the appropriate level of separation. Some equipment may be more sensitive to interference than others, and the manufacturer's recommendations should be followed. 11thly, regular inspection and maintenance of instrumentation cable runs are essential for ensuring that the separation requirements are being met. Cables should be inspected for damage, and grounding connections should be checked for tightness and corrosion. Any issue should be addressed promptly to prevent interference and ensure the reliability of the instrumentation system. 12thly, documentation is critical to verify that the instrumentation circuits meet the required separation criteria. Cable schedules, wiring diagrams, and grounding plans should be maintained to provide a clear record of the system configuration. This documentation can be invaluable for troubleshooting problems and making future modifications to the system. 13thly, the code also addresses the use of intrinsically safe circuits in hazardous locations. Intrinsically safe circuits are designed to limit the amount of energy available in the circuit to a level that is too low to ignite flammable gases or vapors. The code specifies requirements for the design, installation, and maintenance of intrinsically safe circuits to ensure that they remain safe in hazardous locations. 14thly, another consideration is the routing of cables near sources of electromagnetic interference such as motors, transformers, and radio transmitters. These devices can generate significant electromagnetic fields that can induce noise in signal cables. The code specifies minimum separation distances between these devices and instrumentation cables to minimize interference. 15thly, the use of fiber optic cables can provide a solution to interference problems. Fiber optic cables are immune to electromagnetic interference and can be used to transmit signals over long distances without degradation. The code specifies requirements for the installation and termination of fiber optic cables. 16thly, surge protection devices are installed at both ends of the instrumentation cable. 17thly, regular testing of the instrumentation circuit must be done to comply with the required separation criteria. 18thly, when installing instrumentation cables in wet or damp locations, additional precautions may be necessary to protect the cables from moisture. The code specifies requirements for the use of waterproof connectors and enclosures to prevent water from entering the cable. 19thly, the use of shielded twisted pair cables can provide additional protection against electromagnetic interference. Shielded twisted pair cables have a metallic shield that surrounds the twisted pairs of wires, which helps to block unwanted signals. The code specifies requirements for the grounding of the shield to ensure that it is effective in minimizing interference. 20thly, the National Electrical Code is updated on a regular basis, so it's important to stay current with the latest requirements. The code is published by the National Fire Protection Association, and copies can be obtained from their website. 21st, the authority having jurisdiction, which is typically a local electrical inspector, has the final say on whether or not an installation meets the requirements of the National Electrical Code. It's important to work closely with the authority having jurisdiction to ensure that the installation is compliant. 22nd, continuous flexing and movement of cables can lead to wear and tear, potentially compromising the integrity of the shielding and insulation, which impacts signal isolation. Consider the mechanical stress on cables, especially in robotic or automated systems, and ensure appropriate cable types and management techniques are employed. 23rd, it is very critical to select the correct materials and cable types for environments that have corrosive properties. Chemical exposure can degrade the cable jacket and shielding, leading to issues in separation. The National Electrical Code Section 727 is an essential reference for anyone involved in the design, installation, and maintenance of instrumentation systems. By following the guidelines in this section, it is possible to minimize interference and ensure the reliability of these systems. Remember to consult the latest version of the National Electrical Code and any applicable local codes and regulations to ensure compliance. 24th, regarding changes and updates, remember that NEC is updated every 3 years, so regularly review the most current edition to stay abreast of changes to Section 727 or related articles that might impact instrumentation cable separation. 25th, it's also essential to consider the long-term maintainability and accessibility of the cable runs. Proper labeling, documentation, and physical layout contribute to easier troubleshooting and future modifications, while still adhering to separation requirements.